All right, I think we're good. All right, so thanks for coming, everyone. This week, we'll be talking about the Understanding Deep Learning, Chapter 13. We'll be doing graph neural networks. Yeah, we'll just get started. So just to start, to lay the groundwork, so what is a graph? So graphs are made up of nodes or vertices, and they're connected by edges or sometimes called links, and so that's what this is. So all of these blue parts are nodes, and then all of the green parts are edges or links. And so some of the examples that they laid out in the book were like physical addresses. I see a chat. Hang on. All right, we're good. I just want to make sure I'm not leaving them in the dust. So you might have something like physical addresses. So we have all of these locations, and then there's roads that connect all of them. So that's one example they laid out. And then another one is atoms. You might have an atom, and then it's connected by chemical bonds, and then that makes up a molecule. And these are very often sparse. So you don't have every atom is connected to every other atom, and every address isn't connected to every other address. You only have some roads that lead to other addresses. And so one side thing to think about is like with images, you do still have a graph, but the graph is only connected to the pixels that are neighboring it. So you have one pixel, and then you have top left, top right, et cetera. And so they're locally connected. So most, like, you can represent pretty much anything as a graph if you just get the connectivity right. So there's various different kinds of graphs. So you can have an undirected graph. So that's like when you connect with someone on a social network. So you connect both ways. One person is connected to the other, and there's no directionality to it. Or you can have a directed graph. So it's like following someone on Twitter or something like that, where it's like, I'm following you, but you're not following me necessarily. So there's a directionality to it. And you can have heterogeneous graphs where you have various different kinds of nodes and edges and relationships. So here's kind of the various different sets. So this one is like the social network one, where it's undirected, and Alice and Carol are both connected to each other. Or you can have something like a citation graph, where there might actually be some directionality to it. So this paper cites that paper, but it doesn't go the opposite direction. And then you can have something like this, where you have heterogeneous, where you have different kinds of relationships that are represented there. And so you can have different kinds of nodes, and you can have different kinds of edges as well. So like Intel is a company, but Aaron is a person. And so there can be different types of nodes and different types of edges, and that connects in a very rich way.
You see that the same nodes are connected, same links.
Yeah. So like with this one, Aaron is connected to Alice because they have multiple different relationships together. So Aaron works for Alice, but also loves Alice, apparently. So you can have multiple different links connecting them with various different relationships. So next we'll talk about the graph representation. So these nodes are interesting, but typically they also have a whole bunch of metadata that's associated with them. So like on a social network, you might know a person's age, where they live, a bunch of stuff like that. And that can tell you a whole bunch of stuff about that specific node. And so you want to capture that information and then pass it through your network in some way. And edges can also have a bunch of information associated with them. So you might have roads have different lengths, and they might have different number of lanes and stuff like that. And so edges can also encode a whole bunch of information. And so the features that you get out of that can become node and edge embedding. So it captures those features that you're pulling out. And so here's an example showing like, here's the embedding that's associated with node 2, and here's the information that's associated with that connection. And then you can have an adjacency matrix that's telling you how these things are connected up. So 1 is connected to 3, and we can see that over here. And then you can also have the embedding matrices for the nodes and the edges. And so this is saying for node 1, here's the information that's associated with it, and it's that vector there. And so this is showing the relationship between them, and this is showing the information that's associated with the nodes and the edges. Um, so we represent those as the matrices A, X, and E. And so that's the adjacency matrix, and that's the node embeddings and the edge embeddings. So that's A, X, E. And so this can sometimes be represented by this full adjacency matrix, but also a lot of the time it will come in the form of just a list of connections. So you just say, here's this person, they're connected to Alice and Aaron and whoever else. And that's much more dense than this, because if you have something where it's like, I have 1 million users and each person is only connected to 200 of them, then you're just wasting this massive matrix with a whole bunch of sparsity. And so there's different ways to represent that. You can have dense or sparse adjacency matrices. And then X is this over here. And then E is this over here. That's the edge embeddings. And this visualization here is showing that we have the node 6 and it's everything that it's connected to. So if we went over here and we looked up in the right spot, we would see that 6 is connected to 5 and 8 and 7. And we can also do this interesting thing where we can basically multiply this out and we can get the second layer connection. So we can say, what is it 2 hops away from? And that can give us a deeper representation. So this is showing, okay, we're only connected to 5, 8, and 7 on 6, but if we go a second hop away, we can look at all of these 2-step out connections. One of the most important things about this is the permutation invariance. So if you shuffle things in a graph, you can still make it make sense if you keep track of the indices. But in a lot of other stuff in ML, it doesn't make sense if you shuffle it. So like if you shuffled up an image, all of a sudden your image is nonsense and it's very, very hard to learn from. But with graphs, because we're keeping track of the indices, you can actually keep everything lined up and it's not a problem. And so images, you shuffle them, it becomes nonsense. Tokens, if you shuffled up language, it becomes nonsense. But if you do this correctly with the graph neural networks, you can have it not care at all. It's perfectly fine. And so this allows us to do a bunch of interesting things where you can do stuff with sets. So if you have something that's outputting a bunch of values, it can output it invariant to the ordering. So a lot of machine learning, if you put the input in a certain order, it's expected to always come in that order, and your output is also expected to always be in that order. And so this gives you a lot of flexibility, actually, when you represent it like that. So there's a bunch of different tasks that you can do with graphs. So one of them is graph classification. So you have the entire graph and you want to say something about it. So you might have a molecule and you want to say, is this toxic, non-toxic? You might want to say, what's the melting point? And so you look at the entire graph and then you come to some conclusion about it. You classify it, you do regression on it or something. But at more granular level, you can also do node classification. So for a specific node, is that node some class? Is there some regression associated with it? And you can also do that with edge classification. And so these visualizations, this top one is graph classification. So you do some work with it, and then you end up getting the sort of representation of the entire graph. You combine it in some way, and then you get this embedding, and then you apply some classification layer at the end, and you say, classify it 3 different ways. And node classification is different because you're looking at these individual nodes, and you're trying to come to some conclusion about the individual nodes instead of the entire graph all at once. And then the edge prediction is kind of interesting because this is like on a social network, if you're looking for like, who's the person who I know and I'm not connected with them yet. So this can kind of predict saying like, I expect there to be some connection there. Maybe it's missing in our data, but there is actually some relationship here. And so this edge prediction can take that and say, these 2 nodes look related, so they should be connected in some way. Any questions? So looking at graph convolutional networks, so these are interesting because it aggregates information from all of the nearby nodes. So if we look at this pattern, so this is the initial setup. We have a certain graph and we have the embeddings associated with them. And then we pass it through one layer of the neural network or the graph convolutional network. And what happens here is that it will apply an aggregation to all of the connected nodes. So like imagine we start with, let's start with 1, for example. This aggregation step is going to take a sum of this embedding and this embedding and this embedding because they're all connected to 1. And so that's this piece here. And then it's going to apply some layer on top of it. You can have multiple layers or it's just a single one. It just depends on how you set up your network. And so these all aggregate into this node, and then at the same time, we're going to apply that same layer to node 1, and then we're going to sum it all up. So it's going to be the layer applied to this, and the layer applied to this, this, and this added up, and then you get that sort of condensation of all of the connected information. And so that's just one layer of it. But if you actually go a second step, if you think about it, the next step, you're going to go one deeper because you're going to be looking at 3 and all of its connections and 5 and all of its connections and 4 and all of its connections. So when you're going through this, you're going one layer further out in terms of the connections every time because you're doing that aggregation step where you're flowing the information to all the way back to this node, basically. Well, that's part of the we'll talk about that on another slide, but that's one of the major challenges is as you add more layers, you're actually going to increase your connectivity because every layer you're expanding out one hop basically. And so eventually, like by the time we get to here, we're actually looking at the entire graph because everything's at least 2 hops away. And so that can be good, but it can also be bad because if you have some connection that's connected to Elon Musk on Twitter and he's connected to 2 million people, then all of a sudden you're aggregating like the entire graph and you're not actually doing what you want to. So yeah, that's this equation though, basically saying for the next layer forward, we're going to take an aggregation of all of the connected layers and then apply some dense layer on top of it. And then we're going to also do it for the initial node that we're looking at and apply that layer and then some bias and then some activation on top of everything. One other piece, so the parameter sharing. So the interesting thing about this is that this layer is actually the same everywhere for all of these different nodes. So if we were doing this with like some other neural network setup, we might have a different parameter for every single node, and that would end up being this massive, huge amount of work because you have to learn parameters for every single node in your network. But in this, the parameters are shared. So there's a certain layer that we apply to all of these nodes, and it's shared, and we do that the same for the hidden as well. So there's some layer that will turn these embeddings into better features every hop, but it's the same one for every single node. We're not learning one per node.
Keeps it a little bit an order of complexity.
Yeah. So now we have I see chats. Hang on. Slide is cropped. Hang on. Can you guys see that or is it cropped? It's good? Okay. Okay. So now we have inductive versus transductive. So inductive is this setting where we are learning from labeled data. So all of our points are labeled, and then we have like, for example, we might have all of these are labeled, and then we're trying to predict on some brand new graph that has unknown values. And then in contrast to that, in transductive, we might have a mixture of labeled and unlabeled. And so like in this scenario, we have some of these are labeled and then some of this stuff is missing. And this is very common in a lot of graphs because like you don't have full connectivity and awareness of everything that's going on. You don't know everything that exists in the universe. There's always missing data somewhere. And so a lot of the time, these transductive settings, you're trying to actually predict those things that are missing. So like there's a connection that's missing, or some user is missing some information, or they should fit in some group and they're not in that group yet. And so these are kind of two different ways of two different problems that you might come across. So here's an example of some node classification. So we have this big graph and it's got some labeled and some unlabeled, and we want to learn from the labeled stuff and then go do predictions on the unlabeled. And so it's difficult to fit an entire graph. So if you have something huge like Twitter or Facebook or whatever, it's difficult to hold that whole thing in memory and then do any operations onto it. And so the clever trick that you can do is instead of training on the whole thing, you make instances of just the individual node and then its connections, and then you can make batches out of that. So like, for example, you start over here and you're saying, I want to predict this specific node. So then I'm going to look 2 away from that. And then after that, I'm going to look at the connections as well. So you've kind of constrained your problem to only be looking at certain of the nodes. You're not looking at all of them all at once. So this is the thing earlier. So even if you do that, if you're going, I'm going to do 1 layer, 2 layers, 3 layers, 5 layers, eventually you're 7 layers away and you're connected to everything again. And that can end up being a problem. So the trick around that is this neighborhood sampling. And so this is kind of the unconstrained saying, I'm going to start here, and then I'm going to go to all of the connections, and then I'm going to go to all of the connections, and then you can see it like fills out the whole graph, basically. You're looking at the whole thing again. And the alternate is with neighborhood sampling, you might only look at 3 neighbors every hop instead. And so you start with 1, and then you're only going to the 3 connections, and then you can go to 3 other connections. And so this constrains it. So you can do a whole bunch of layers, but you're not necessarily doing full connectivity, saying I have to connect to 1 million different nodes. You're still only connected to 20 or 30 or something like that. Another approach is graph partitioning. So they had a little section where they were talking about you can split the big graph into some subgraphs, and then you say, I'm just going to do classification on that. And that's another way to do it. So the graph layers, initially when we talked about it, we were looking at the one slide, and the aggregation, that's actually a very important step. In the initial formulation, they were showing just summing them. So if you have 3 nodes that are connected, you just add them all up, and then that's the information that's flowed through. And that's good, but it can end up with problems where if you have a lot of connectivity, then you're just summing this huge value. And that can cause problems if you're building this huge graph that has big sums. And so an alternate is you can take the mean. So that's an obvious option. So you just say, I'm going to divide by the number of incoming nodes. You can take the max. You can do residual connections. There's different normalization schemes, but a really popular one now is attention layers. So you have, instead of everything just being weighted equally on the way in when you're doing that aggregation, you can have some learned process where it's saying, I'm going to take more information in from this node than that node because I think that this is relevant to our classification. So you add some attention layer in there, and then it will figure out what's the best weighting of this information in order to flow it through properly. So the last section, they were talking about edge graphs. And so the trick that they were talking about is you can basically turn any node graph into edge graphs by turning the connections into nodes of their own. And then for every edge with the shared node, you also add a new node. So this is the original graph. And then what you're doing is you're turning all of these into their own nodes again. So that's this 2, 5 node, 2, 3, 1, 3. So you're adding those as new nodes, and then you can flow the information along those, and they're all kind of treated similarly. So that's how you integrate the information from the edges and the nodes at the same time. And then on this, you can see that they actually added some additional connectivity. So like 1 and 5, 1 and 4, those are connected because they're both connected to node 1, actually. Yeah. Yeah. So this is just the edge graph. This is kind of the combination of the two, and then this is the node graph. I think that's for the edge graph. I assume if you're just, there might be some application where you only care about the edges, you don't care about the actual nodes, but I'm not sure. They didn't have an example of that, so I don't know. But yeah, I think that's all I have. I will check the chat.
I did like the transductive and the inductive part.
Yeah.
Okay, if I ask him to go over it one more time.
Yeah. Yeah. Did you have some? So the way it's set up, imagine all of these are different molecules that we have, and we know some outcome from them. And then we have a new molecule, and we're saying, do that same process on this molecule. So figure out its melting point, for example. And so that's one way of doing that, the inductive. And then the transductive is like, we have this big graph, and we want to figure out, like, we have a new user, we want to know who they are. Like, we want to know some factor about them. We want to know if they enjoy sports or something like that. So we're doing some classification on them. And so we know that they're connected to this person and that person and this other person. And based on their connections, we probably know they like sports or something else, and we can make some inference about that missing field.
You have to have that series of information for the edges that lead into what you're trying to figure out for that node. So you're trying to figure out if they won those sports, but you have to have the other two matrices filled out, like you do for edges. You see my point?
You need to have some knowledge. You have to.
Like the cut for the white sides, but on the edges you all have information about each node. You have to have edge information feeding into that node.
Yeah. Yeah. So yeah. Yeah. So you have to have some flow of information to the node. It can't be like a complete orphan, but like, this is a new user. They added this friend and that friend and that friend and that friend and that friend. And just knowing by association, this person follows this groups and they're posting about these kinds of sports and whatever. And so knowing that these two are connected and this person is associated with that, then you can flow that information into them.
Well, for the inductive setting, for the test graph, you need to do something.
No. You have to have some information on the node embeddings and the connections, but you don't necessarily, like this, the blue and the orange is showing some sort of classification. You don't necessarily need that for this. You just need some embeddings and connections for, yeah. So graph networks can be used for pretty much anything that involves these sort of social networks or molecules, or like if you really think about it, graph convolutional networks can make up basically anything. Like a graph convolutional network can represent an image CNN. It's just about laying out the connectivity and everything correctly.
They're all layers.
Yeah.
Like, for example, like that bucket trying to the edge, then they have it. Then the model kind of the three dots.
It can be a mixture of all of that stuff. But typically it's like the social network type stuff. But the these embeddings here can represent like anything. The embeddings could be, I passed this through an image neural network and now I have some information about an image, or it can be I did text and then I passed through some encoder and now I have this embedding here. So the graph can represent all kinds of different stuff inside of it. Well, on the first layer, basically, when you're encoding these embeddings, you can do that for every single node. And then after, when you're flowing that information together, that's when it doesn't matter anymore. So you could encode some image. So it's image of a dog, you pass it through ResNet 18, and then you get some vector out. That can be this vector, actually. Yeah. And then the interaction between all of those is where the graph convolution comes in. Yeah. In all of my years doing machine learning, I have not had a reason to use graph networks. I know that people do them all the time, but I've just avoided them somehow. So yeah. So it's interesting though, because you can do just about anything with them, but the difficulty comes in a lot of the specialized things are a lot faster. So like you could make a CNN out of a graph convolutional network, but all of our CNN code is so optimized, there's like no reason that you ever would. But the graph convolutional network can represent like anything. It can, as long as you set the graph up correctly. Yeah.
Ryan, some questions in the chat.
The problem is usually like building the graph itself. Like that seems like fun. Because like it's often just like they're kind of a pain in the ass to like store, and they're a pain in the ass, and like the tools for actually manipulating them are not very well developed, and like putting together the data is often like kind of manual and annoying, and like that's I think the problem is making the graph. Yeah, like they actually what?
Some kind of a thing, the package you instantly store and he was talking about the computer, that's why I asked.
Yeah, I'm not saying that's not good.
Like the location part is not.
But like with images, for instance,
Yeah.
like you just take a picture and then you have with the graph, you actually have to like do all this work to build.
And a lot of the time, it's not like the images where you can use the label someone else did. If you're building your own graph, it's because you want to represent your own connection. So it's unlikely that you have well, and building, right?
You have to come up with relationships.
Yeah, and you have to find those and build it, right? So even research in graphs tends to be limited, like right in the medical space, there have been attempts to use like medical ontologies to provide structure onto.
Why are you trying to hold up the other ones or conversation?
It is tricky, I guess. So sounds like you've tried it.
Yeah, I wrote a textbook on.
Okay. All right. You'll have to send us the link.
Yeah, well, it's currently